Hello, my name is Gary Bastian, and I'd like to welcome you to Exchanges at EntelMed. Today's guest is Dr. Keith Burgess. Dr. Burgess has a master's degree and PhD in electrical engineering and a bachelor's degree in physics. He has spent the last 20 years working on advanced engineering projects at Northrop Grumman and Lockheed Martin. Most notably, he developed the radar system for the F-35 fighter jet. Without further introduction, here is my conversation with Dr. Keith Burgess. Dr. Burgess, you have a master's degree and a PhD in electrical engineering, and you also have a bachelor's degree in physics. You've worked on a tremendous number of projects over the course of your career. Can you tell me a little bit about the most exciting project you worked on and why you were so passionate about it?
I've worked on a lot of fun things, things involving radars and sonars and target classification, um, sickle cell anemia analysis, um, how gamma rays affect what we observe from other stars, so it's astronomy. But one that was mildly, only mildly related, but is very, very interesting, I think, was modeling the pinna, which is the shape of your ear. And the goal, say up front, was for computer games. And I'm personally not a big computer game player, but that was the market. And the idea is that if I have some speakers in front of me, or you could have more than two speakers, so you could have five speakers, you could have a surround sound system, but with two speakers minimum in front of me, I can make sounds come out of those two speakers so that when they interfere in one ear and then when they interfere in the other ear, that the shape of those sounds and the delay of the sound coming to those ears makes your brain or is physically indistinguishable to your brain from the sound that would come from, say, over here. So the idea, of course, the market is you're playing a game and you're in a tank and you're shooting at somebody. You probably shouldn't be shooting at them, but that's the way the game works. And you want to know if somebody's shooting at you from over there, so you can spin your turret around and shoot back at them. And anyway, the interesting part is the modeling of the ear and collecting measurements, very high resolution acoustic measurements of how sound gets into your ear, figuring out how it's all processed by your brain and the delays that are put onto the sound waves by the shape of your shoulders and your head and your ears and all of that. So it was a fun project.
You also worked at the MIT laboratory. What were some of the projects that you worked on at MIT?
A lot of it was ultimately related to radar, and the idea is that you've got an adversary at the time. The adversaries change in time, of course, but you've got an adversary who's shooting something at you. In this case, it was intercontinental ballistic missiles, and they don't just shoot missiles at you. They also try and trick you. They shoot other stuff at you, missiles that are balloons and missiles that just throw lots of tinsel up in the air that looks to your radar like lots of flashlights beaming at you up there, and you have to figure out the difference between the two. So we use pattern recognition algorithms to figure out what was the real missile and what was not the real missile, because you don't need to worry about the tinsel falling on you. You need to worry about the nuclear warhead. So that was, is that idea. Or the observation of trying to figure out, well, what is it? What is this out there? So it was the Russians at the time. They're shooting something from one point to another. They're doing their tests, and we're trying to figure out, well, what is that? How big is it? How heavy is it? What are its characteristics? So we can categorize it. And so you're collecting this relatively noisy radar data, and you have to pull through it and figure out what actually that thing is that you're looking at. And there's a lot of physics in that. For instance, when something is lobbed, it's going through different layers of atmosphere with different thicknesses. The atmosphere gets thinner as you go higher, and so not only does that affect the drag on the object, but it affects the changes in its spin and precession. So the object changes its motion as a function of the atmosphere and its weight. So you can infer one thing from the other. So a lot of interesting physics in all of that. So, but ultimately, the category it was at the top level, radar and artificial intelligence is really, I guess, I have to say so. It's radar algorithms and artificial intelligence. And ultimately, if you boil down just about everything I've done, it comes down to the category of algorithms and artificial intelligence, because I apply all of these categories to it, but it's really the same thing under the hood.
You're also an expert in sensor integration. Can you explain to us what is a biosensor and how will biosensors be used at EntelMed?
Let me answer that question by starting with the type of things that can be sensed. And there's things that a doctor on one end, analyst or doctor, can extract information from symptoms somebody's having. For instance, things like allergies, asthma, bronchitis, arthritic pain. Uh, some of these are from you. You're the sensor. So when you say my back hurts, where does it hurt? You can describe where it hurts. That's you being the sensor, but there's other things you could do, like colds and flu. You can measure your body temperature.
Mm-hmm.
If there might be chemical things that you could test for, you can look for high white blood counts, for instance. I'm not suggesting that there's going to be a mechanism that a person's going to take their blood apart and do an analysis, but there could be an equipment that extracts a few drops of blood and makes an analysis of those things. Other situations that infections, insect bites, laryngitis, conjunctivitis, rashes, respiratory infections, sinusitis, cellulitis, sore throats, sprains, bladder infections, sports injuries, vomiting. There's a whole list of things that can be described to a doctor. Then there's the issue. But then there's the issue of, well, which some of those can be collected with external sensors. In particular, the simple ones are temperature, blood pressure, pulse, oxygen levels in your blood, glucose levels, so certain chemical signatures. And so when we say biosensors, we're usually talking about those things that we can put on a person or extract some of their blood or something else. I have a friend who works for Cologuard in Madison, Wisconsin, and they're looking for colon. They're trying to replace colonoscopies and other things using stool samples that you send to Madison, Wisconsin, and they just have an automatic process in a very clean room that chugs through the whole thing and figures out if you need to have a colonoscopy. So, and believe me, it's a desirable. Colonoscopy means you have to go somewhere. They have to put you out chemically. You have to put you to sleep, and it takes a lot of a doctor's time. And it's still necessary, but if you can have a test that says, there's a 70% chance or an 80% chance that you do have it, and there's a 70% chance that you don't. I'm sorry, it's a 30% chance you don't. You should go and have a further test. Already, you've reduced everybody from needing a colonoscopy to a small set. So that would be an example of a sensor, which is a chemical strip that is something that is replacing at least exploratory surgery in a sense.
Can you explain why doctors and hospitals will use biosensors in remote patient monitoring, and what capabilities do these sensors currently have?
We've already got a number of fields, telefields that are coming about by existing sensors. There's teleradiology, passing radiological results, telepsychiatry, teledermatology, scan your body, look for automatically look for lesions, but if nothing else, you can at least transmit the image to somebody remotely who can view them. Teleophthalmology of your eyes, telenephrology from kidneys. I wrote this down, by the way. Teleobstetrics. Obviously, we're not going to be delivering babies, but you can monitor a baby's heartbeat remotely, and the doctor can listen to it. Are there aberrations? do we even need the doctor in this? Maybe we can automatically listen to the baby's heartbeat, and maybe instead of just doing it once a day or once a week or however often you have a prenatal exam, we could be doing it constantly and to pick up warning signs. Then there's telepathology from images and videos that you're taking, telerehabilitation, physical therapy. So a number of these have already started, but the ones that are at the forefront right now are looking at oxygen in the blood, because you can do that by just putting infrared through your finger. So the sensor is just collecting how much infrared radiation is passing through your finger, your body temperature, blood pressure, pulse, which is your heart rate, and then there could be sleep patterns. You know, how deep are you sleeping? Are you snoring? What sounds are in the world around you? I mean, some of these exist in iPhone apps now. Mm-hmm. So those will be, that's really that's the low-lying fruit. It's already out there. The sensors already exist. And the idea of this company isn't to try and design those sensors. There's a lot involved in that, and other people are doing that. The idea is to integrate them all and bring them all into and have them work with each other. So we can collect information from multiple sensors and make diagnoses that you would feed to somebody. You can extract information that you feed to somebody that you couldn't from any of the sensors separately.
I understand you also have extensive experience with advanced image processing. Can you explain to us what is advanced image processing and how could it be utilized by, say, a doctor in a rural area reading an X-ray?
That's the field of teleradiology. So, and this is what we bring in economics. If you had a magic wand, then whenever somebody had an X-ray in some rural clinic somewhere, then there would be the equipment to measure, to take the X-ray, for instance, and then you'd have a doctor right there, right then, who could look at it and make an analysis. But the economics of that are that doctor would be very unbusy a lot of the time, or they would have to have other specializations, which is a level of inefficiency, because then they have specializations that they're not utilizing all the time. Mm-hmm. So at the front end of this, the equipment to collect that information, the sensors themselves are cheaper, and that can be collected. And then we can move the doctor to some other location where she can go through these radiology images in a room and just hit them off one at a time. And it's a 9-to-5 job where the doctor is working from her, it could be from her home or a nearby office, not a lot of commute time, and they don't have to go see a lot of different locations. And then once we have that sensor information and we're going to present it to the doctor, we can already run it through algorithms that look for certain things, like, well, why was the X-ray taken in the first place? Was it a broken bone, or was it looking for some sort of cancer? Are we looking at breast tissue for breast cancer, for instance? And so those things can go through algorithms and flag things. And at this point, we're not replacing this radiologist at all. All we're doing is we're putting an electronic circle on an electronic transmitted image that says, hey, you look at the whole thing, but focus on this. And here's the reason. This is category A16, which means a likely lesion in the lung, for instance. So you would just feed the doctor information. So what do we have here? We have sensors collecting information, storing, transmitting that information, processed to somebody remotely who's doing analysis with information that's supplemented by the algorithms. We come up with a conclusion, and there's the economics of the whole thing, because now one doctor can supply many different areas, keep busy more often, and so there's no commuting time, but more importantly, now we've got a queue that we feed the doctor, so the doctor isn't playing Sudoku on her phone or whatever the heck they do when they're not busy. We can keep them busy more often, which is where we get more efficiency in the system, and then we can decrease make their job easier and decrease the false alarms, the times when they're wrong, by helping them by pre-processing the data that we feed the doctor.
As you're kind of describing that, it sounds like the flow of communication is a big component of the portal. What is EntelMed doing to facilitate this communication, and what will that actually look like within the portal?
My personal interest is in sensors and systems and integration, but there's a whole other side of this company that uh, is providing perhaps more value than that, and that's the whole interface between the customers and the the interface between the customers and the providers, and in particular, the whole concept of an avatar. So having an automatic mechanism for communicating with a patient, extracting information from their voice and their stress, and uh, you know, listening to the words they're saying, converting it into text, having it processed and categorizing it, and figure, well, does this person need to talk to doctor type A, B, or C, or D, and then passing that information, then you know, passing that information to the appropriate doctor. So that whole idea of having a communication mechanism and how that information flows from patient to provider is itself a whole nother specialization that we're tackling, and that's interesting. And you'll need to speak to other people in the company about that.
That's fantastic. And, I think that's a great place to actually end our interview today. And I just wanted to say, Dr. Burgess, thank you for spending the time with me today. It was a great pleasure hearing about your experience and your expertise. And I really look forward to the work that you're doing at EntelMed.
Oh, thank you. I appreciate your time, and this is an interesting field. There's a lot of interesting things that are happening and that are going to happen, and I'm looking forward to seeing it myself.